Cursor gave a team of AI coding agents an 835-page SQLite manual and one job: build SQLite in Rust. The agents could not see SQLite's source code or tests, run SQLite itself, or use the internet. That manual was their only map. The first team looked wildly productive. Before Cursor stopped the run, just short of 2 hours, it had made about 68,000 commits, recorded code changes, and piled up more than 70,000 merge conflicts, places where those changes collided. Yet its SQL result score barely moved. The code counters were racing. Useful results were not. Then Cursor changed the system coordinating the agents and ran Grok 4.5, the same model on the same task. 4 hours later, this team reached about 80% on that SQL result check. A stronger model cannot explain the jump. The model name never changed. The team system is the difference we now have to understand. That 80% is a clue, not yet a conclusion. Before we open the team system and see what changed, we need to pin down exactly what the number measured. Open the sealed scorecard and picture one test. A SQL query goes in. The engine's result slides beside a stored expected result. If they match, that query passes this check. Cursor built its percentage from a held-out SQL logic test corpus, a collection of checks kept hidden from the agents. Now run the same check on two engines. Both return the expected answer, so this score marks them alike. But one may be fast while the other is slow. One may coordinate two users while the other fails when their work overlaps. SQL logic test is designed to judge the answer, not speed, or what happens when database work overlaps. So when Cursor says later runs reached 100%, read the number inside this boundary, 100% of Cursor's undisclosed held-out SQL result corpus judged by an unpublished evaluator. That is meaningful evidence that the engines matched this benchmark. It is not 100% of SQLite, and it does not certify a production-ready drop-in replacement. With the finish line now fixed, we can open the part that changed, the agent team. Start with the whole assignment. Turn the 835-page manual into a working database. Instead of handing that same enormous goal to every agent, one root planner owns it and splits it into branches. For example, one branch could own SQL queries. A subplanner narrows that branch again until one leaf says, parse one select statement. At that leaf, the job changes hands. The planner owns the design and decomposition, but is not allowed to write the code. A worker receives the one bounded task and implements it without carrying the whole database plan. The planner owns the branch, the worker owns the leaf. Zoom out, and the split becomes visible. Planners keep the broad architecture. Each worker keeps the local implementation in front of it. Cursor's hypothesis is that this protects the big decisions from code-level clutter while the tree's boundaries keep ownership explicit. Because the new harness changed several mechanisms together. The experiment does not prove that this tree alone caused the gain. Follow the token counter down the tree. In every run, the workers writing code used at least 69% of all tokens, and usually over 90%. Most of the tokens flowed through the many workers below, not the few planners above. Now compare two runs from the controlled experiment. The team with Opus 4.8 planners and Composer 2.5 workers cost $1,339 in total. The team using GPT 5.5 for both roles cost $10,565. Putting an expensive model in the few planner seats did not make the hybrid the expensive system. Its total bill was far lower. That is the leverage. A planner's choice does not end at the planner. It shapes every worker task below it. Better judgment can spend more on a few planning tokens, yet prevent a much larger stream of worker tokens. So the practical question is not, which model is cheapest? It is which model belongs in which role, and how much work will that choice create? These two runs support that rule, but they do not prove planner quality alone caused the gap. The model mix changed too. Put the two teams side by side one last time. In the failed swarm, adding agents adds more arrows of activity, but the shared direction splits into incompatible paths. More hands multiply motion. They do not preserve the decisions that make separate pieces fit. In the ownership tree, direction stays narrow at the top. Only after a planner gives each leaf a clear boundary does execution fan out. That makes judgment the leverage point. One choice near the root shapes many tasks below, so its true cost includes the work it creates. Now pull back. The detailed specification supplies the target. The ownership tree divides the work, and the SQL-result check tells us whether the engine got the measured behavior right. Together, they show the narrow promise of a large agent team. Useful progress around a measurable task when ownership keeps its decisions coherent. That is a coordination result, not certification of a new SQLite. The real scaling trick is not adding agents. It is preserving judgment as the work spreads.